Hello everyone, welcome to today's webinar. I'm Catherine Dole, a science writer, and I'm here today for Chemical and Engineering News Media Group. I'll be moderating today's event. This webinar is titled Rotary Evaporators, Redefining the Way You Evaporate, and is being sponsored by Heidolph North America. C&EN works with sponsors to identify topics of interest and value to C&EN's audience and consistent with C&EN's mission to provide news and analysis of the chemistry enterprise in a timely, accurate, and balanced fashion. During the webinar, you can adjust the size of the slides on your screen by grabbing the lower right corner with your mouse. If you need technical assistance, please look for the Help widget at the bottom of the screen or type your query into the Q&A box. If you're disconnected during the webcast, please log in again according to the instructions you received earlier. You're encouraged to contribute to the success of this webinar by asking questions at any time during the presentation through the Q&A box on your screen. The questions will be answered at the end of the presentation, and as your moderator, I will be posing as many as time permits. Please note that C&EN does not endorse any company, products, or services that may be mentioned in the webinars, and that each webinar will be archived at C&EN online after the live webcast. The presentation today is being sponsored by Heidolph North America. Heidolph's goal is to give our customers the ability to focus on their research. Accomplishing this is done largely in part by providing best-in-class service and support for solution-oriented equipment. Heidolph's product lineup includes a full range of chemistry and biology tools designed to increase lab productivity. During the presentation today, we'll hear from Nathaniel Kunzer, who is a product specialist at Heidolph North America. Nathaniel is the North American product specialist for all rotary evaporator products. He has spent 5 years working with benchtop and industrial-sized rotary evaporators for both research and process scale. He's based in the North American headquarters in Wooddale, Illinois. We'll also hear from Jürgen Heider, who is a product manager, rotary evaporators at Heidolph, Germany. Jürgen is the global product manager for all rotary evaporator products and is based in Schwabach, Germany, which is Heidolph's headquarters. He studied in Germany as well as in the UK and is responsible for market-driven development processes to guarantee customer satisfaction and the related market success. With more than 12 years of experience in inside sales, marketing, and product and market development within the field of laboratory products, he knows the opportunity and challenges that users of rotary evaporators face day by day. He works in close cooperation with independent researchers to guide the product development process in a customer-oriented way. I'll now hand the program over to our first speaker, Nathaniel.
Thank you, Catherine, for the introduction. I'm Nate Kunzer.
Thank you, Catherine. Thank you, Nate. I'm Jürgen Heider, and I'm looking forward to have that session today with you, and we hope we can give you some more hints and tips about rotary evaporation.
So the things we're going to be going over with the rotary evaporator today is understanding the basics of rotary evaporation, how to increase the efficiency of your distillation, maximizing your throughput, working with different samples and types, minimizing your contamination in your samples, sustainability, why and how to upscale, staying safe while evaporating, tips, and any questions that you might have on the process. One really important thing to keep in mind with rotary evaporation is that rotary evaporation does not just involve the rotary evaporator itself. You have to think of the peripheral equipment that comes with it that makes evaporation possible. In that case, you don't just have the evaporator, but you also have the vacuum pump and the chiller.
Yeah, with the rotary evaporation, it's mainly about evaporation and condensation of a specific liquid. We always use a vacuum for that. So the purpose of vacuum is that you need a fast-reacting parameter where you can address the boiling point of the first solvent or liquid that you want to separate from the mixture. I mean, all of you may know the principle of a rotary evaporator, but for a good beginning of this webinar, I would go through that with my little animation I did here. So a usual, typical process of rotary evaporation is that you heat up, for example, your heating bath to a specific temperature. Due to the vacuum, you do not need so much high temperatures. On the other hand, you always have to cool down your condensation surface on the left-hand side. This can be done via chiller or via dry ice connection. And if this is also on temperature, you can fill your mixture. I marked it here with two liquids, let's say liquid A and B. And then you start usually the rotation of the flask and you lower down the vacuum. You lower down the vacuum to the point where you hit the first boiling point of your solvent. Here you can use the table that is inserted for every evaporator usually, or also there are apps like our Hei-VAP app that can help you to find the right boiling point. And if you reach the first boiling point, you will see that the first foam here marked in yellow color as liquid A rise into the condenser zone and get collected again. It gets condensated from the cooling and get collected in the collection vessel. So there's an increasing liquid of A on the collection vessel. On the right-hand side, you see a decreasing level of your residual, liquid B in this case, that will remain in the evaporation flask. At the end, you can aerate the system and you can stop the rotation in the heating bath. And in the best case, you have a good separated liquid A and the liquid B. Liquid B can be also solid in case you have a powder or powder drying application. This can be also possible.
So now we're going to talk about increasing the efficiency of your distillation, basically making sure you can distillate as fast as possible without even adjusting the heating or the pressure of your system. There's two different kinds of limits I like to consider. Hard limits, which I basically just think of as things that you consider while you're buying your rotary evaporator, and then the soft limits, what can be adjusted after that point. Some of those hard limits include the condenser surface area and the evaporating flask size, while some of those soft limits are your rotation speed and the angle of your evaporation flask. So that first limit is the surface area of your condenser. You can't evaporate more than your condenser can condense. Otherwise, you're just going to be sucking all of that solvent or that stuff that you're boiling off straight to your vacuum pump without actually condensing it back into your receiving flask. Another important point about that is you're not actually using the entire size of your condenser. You want to be going about 3/4 of the way up. Any further than that, and you're also risking pulling some solvent through your vacuum pump and losing that instead of retaining it. The next thing to consider is the size of your evaporating flask. You want to consider how much liquid you want to be evaporating at one time, along with the size of the flask affecting the entire surface area of what you're evaporating. A larger flask leads to more surface area, which leads to more being able to be evaporated off at the same time. And also, you don't want to be going above about a 1/3 fill on your evaporating flask, because above that will also start to reduce the surface area and can lead to some of the liquid bumping into your condenser. The next way to make sure that you're increasing the efficiency of your distillation is the rotation speed. When you've got a static flask, one that's not spinning, you can see that only at that top level is where evaporation will be occurring. Along with that, you won't get uniform healing through your medium because it's slowly being heated without any turbulence to really mix it together. When you rotate a flask, you're getting increased surface area because you're coating the entirety of the flask instead of just one layer. Along with that, you're also increasing the speed at which your heating bath uniformly heats and the medium inside your flask uniformly heats, leading to much more even distillation and an increased speed of distillation. Another thing to consider with your evaporating flask is the angle that you have it sitting in the bath. If you have it at too pitched of an angle, you'll notice that as it's rotating, you're not using the entirety of your flask. There's less wetted surface inside of it, and it's not all evaporating at the same time. When you have it at a lesser angle, closer to 180 degrees, you'll see that the rotation is pulling the liquid all the way around the evaporating flask, leading to increased surface area, which means more can evaporate at the same time. When you're trying to maximize the throughput of your rotary evaporator, there are some predetermined conditions that you want to make sure are met as you're running your evaporation process. The first one is what we consider the delta 20 rule. The optimal condition for the temperature of your heating bath, the temperature of your vapor temperature, and the temperature of your cooling medium, your chiller fluid, is about 20 degrees between each. So say that you're running the heating bath at 60 degrees, your vapor temperature would probably be 40 degrees, and you would only need your chiller to be at about 20 degrees. So a key strategy in maximizing your throughput is to make sure you're not losing any of the solvent that you're evaporating off. One of the big ways to do this is to not exceed the 3/4 height of your condenser with the liquid that you're evaporating. If you evaporate too strongly, you'll find that some of your solvents that you've evaporated off can get pulled through your vacuum pump, which not only leads to you losing that solvent, but can potentially harm you as it's getting pulled into the environment. The easiest way to stop that from happening is just to monitor it. If you see that you're evaporating past the 3/4 mark on your condenser, you can increase your pressure a little bit so that it's not evaporating as strongly. Or if you're a bit below that 3/4 point, you can pull your vacuum down a little bit to bring it back up to that level. Keeping it around there will really maximize how much you can evaporate off at a time. Another way to maximize your throughput is with modern rotary evaporators. They will typically have a gradient method for pre-programming your evaporation process. What this does is it lets you set different times and different parameters that will be met at these times to allow you to pre-program and optimize your evaporation process. What this also can do with single solvent distillations is if you have a solvent that's prone to bumping or foaming, you can bring down the pressure linearly instead of all at once to try to gently approach that boiling point to prevent any increased foaming or bumping from occurring. What it also lets you do is multiple solvent removal. Instead of either A, slamming straight down to the lowest boiling point or the highest boiling point and evaporating from there and completely boiling and bumping the solvents before it, you can go down to each individual boiling point at a time and evaporate them all off one by one. This will reduce any of the chances of your solvents boiling along the way and mean that you can have a much more efficient and maximized process.
Another very nice feature that many of the modern rotary evaporators offers is an automatic evaporation function. This means these systems will find a boiling point automatically. You do not have to gather the data that you need for your specific solvent to find a boiling point. The system is doing that by the own, and you don't have that much effort. Another advantage is that the very modern systems have a very balanced way to find a boiling point and find it very sensitive, so it also prevents from foaming and bumping.
A refill valve is another way to really maximize the throughput of your rotary evaporator. Every time you have to remove your evaporation flask, that's the time that you're not evaporating. Well, what the refill valve will allow you to do is you pop it into a carbuy or a container with your product, you open the valve, the pressure differential between the inside of the rotary evaporator and your product outside it will suck it up and into your evaporating flask without you having to remove it. So that'll allow you to evaporate 2 or 3 times before having to grab your evaporation flask and actually dump it out, really increasing your evaporation time and meaning that you don't have to fiddle with it as much. When you're dealing with different size samples and types, it's all about finding the right flask for the job. Size-wise, you always want to shoot for about a 1/3 fill level. So if you have 2 liters of solvent or 2 liters of material, you want to be looking for a 5-liter flask, or if you're okay with doing 300 mils at a time, a 1-liter flask might be good for you. You always want to have it sized about right so that you're evaporating at the most efficient level. Now, you're not always evaporating liquids that have solvent mixtures. You might be drying out powders, you might have waxes and solids, you might be looking for something that's more continuous. I'll go into all the different kinds of flask types that might be effective for those applications. When you're evaporating powders, a powder flask is very effective for drying those out thoroughly. If you used a normal evaporating flask, the bottom of your powders can stick to the sides, they don't get flipped over, it's not very even drying, and it can really take a lot longer. If you're using a powder flask, it's got these baffles which will flip over the powder, making sure you're getting even drying all around, and it's not sticking to the sides of your evaporating flask with the bottoms of it wet. It's being flipped over so that it's thorough, even drying. Sometimes you are working with solids or waxes that you can't particularly get in or out of a standard evaporating flask. Waxes you might be able to get in, but they might stick to the sides and be hard to get out. Solids, such as in the culinary, you need a much wider opening to get your product in. So what's available are evaporating cylinders with removable lids. This way, you can pop off the lid, have a hole about the size of your hand so you can put things in it or scrape things out of it if they get stuck to the surface. And sometimes you're just looking to process as much as possible. Well, when you're doing that, you're first going to want one of the biggest flasks you can get. 5 liters is usually the largest you can get on a benchtop. That just means you can fill it as much as possible and be getting as much surface area out as you can to increase those evaporation rates. Something you might consider using in addition to that is a foam break bump trap. What this will do is, if you're evaporating a little faster and you start experiencing a little bit of foaming, a little bit of boiling within a reasonable level, this bump trap will prevent that from making its way into your condenser and contaminating your collecting flask. A big thing to keep in mind, though, is that you still don't want to pass that 1/3 fill line. So if you're using something like a refill valve or you're just refilling it as much as you can, try to stick below that 1/3 level, because if you go above that, it will slow down your evaporation process and potentially lead to it bumping over more vigorously and contaminating that collecting flask. So, harping back on that, minimizing contamination. One of the things you want to try to avoid is getting your product into the solvent that you just evaporated out of it. You want to keep that pure so you can reuse it in the future. Well, bumping and foaming is the biggest offender for contaminating that collecting flask. So there's a couple methods to help prevent that from happening. The first is to just reduce the strength of the vacuum. If you hit that boiling point, your product is going to want to boil. And depending on what it is, what the mixture is, that's what can lead to that bumping or the foaming. So if you take it just a little bit more gentle, it won't evaporate as hard and can prevent that bumping and foaming from happening. Another option is to consider using an RPM pump versus a valve pump. We'll get more into the difference of those later. However, the RPM pump will help in the minimizing contamination because it's always pulling at whatever percentage of its power it needs to be pulling at to keep your desired vacuum level. With a valve pump, every time that valve opens, it's experiencing 100% of its vacuum strength, which can really agitate your liquid and lead to some boiling and bumping in those moments that that valve is open. Another method is going back to the gradients that we discussed. You can more gently pull down to those evaporation points and even evaporate a little slower as there's more of the solvent and a little faster as there's less of the solvent to really hone in on the fastest possible evaporation rate with the smallest amount of bumping. And then lastly, a bump trap is always effective because it adds the extra barrier of space between your evaporating flask and your condenser, while also using some specific techniques to prevent that bumping and foaming from going over. Another way to minimize contamination is to make sure you're not getting outside contaminants or contaminants from places that you just don't expect. Most units are greased and use stopcocks in order to increase the tightness of the unit. In theory, you would think that this would reduce contamination because less is coming in from the outside. However, the grease itself can be a contaminant. That's why there's also options to go greaseless, where instead of using greased stopcocks or greased vacuum caps, you'll be using screwing caps that are sealed in a way to basically function the same way without the grease.
We have some customer that really shows that this principle works because a few years ago when we were also supplying that old-fashioned glassware sets, we faced some requests where customer, for example, in Singapore, asked us where this contamination came from. And after analyzing the samples, we figured out that due to the low vacuum inside of the system, a lot of grease was sucked into the condensating and collecting area and caused that contamination.
So another big concept in rotary evaporation is the sustainability of your methods. Whether you're trying to go greener or you're trying to save cost over time, sustainability is a big factor in rotary evaporation. The biggest example of this is in the way that you decide to cool your reactions. There's two main kinds of methods, either using a dry ice trap or using a coiled condenser. The coiled condenser can either be filled with tap water or using a chiller. The dry ice condenser uses the dry ice. Now, the tap water and the dry ice methods may save you a lot of money up front. They may be easier to use at first. However, over the course of the lifetime of your unit, you'll find that you're either wasting a lot of water or you're constantly using dry ice, and having to refill that all the time can be tedious and potentially rack up costs. That's why a chiller is always an effective method if you plan on doing evaporation for a very long time and you want to maybe spend a little bit more upfront but save cost over time and be able to more dial in on the settings that you want.
If you want to learn a bit more about these different technologies, then you should contact your Heidolph sales specialist, because we are close to publish a white paper about the different methods where we did some scientific tests about the sustainability, but also about the ease of use and the accuracy in evaporation. So if you are interested, please go in contact with your Heidolph contact person. Regarding to the vacuum source for your rotary evaporator, there are two different kinds on the market. The one is a diaphragm pump. This is a valve-regulated system. And the other one is what Nate already mentioned, the RPM-regulated system. The RPM-regulated system is honestly the more up-to-date version of the pumps. The main difference is that the valve-regulated system let the pump run for 100% all the time, while the RPM-regulated system is, on the one hand, more accurate and is only active as long as you need the vacuum. So as soon as your system hit the set vacuum, it would turn off the pump. The other advantage I already mentioned is the accuracy of regulation. So you come very close to your vacuum, to your set vacuum, and you don't have a real hysteresis inside the system. And what we figured out, which is also with our partners from Vacuum Brand, is that you also have a more stable and more efficient evaporation due to it, and you can finish your evaporation processes 30% earlier than with a valve-regulated system. So this is a big advantage if you choose the RPM-regulated pumps. The disadvantage, of course, is that this technology is a bit more, let's say, high-end and costs a bit more also.
So sometimes your process sort of outgrows a benchtop rotary evaporator. In that case, you might want to be looking to upscale. In that case, an industrial-sized rotary evaporator might be more up your alley. What a larger evaporator provides is increased condenser surface area, which we mentioned is one of the limits to how much you can evaporate. Increased heating power, so you can heat more inside your evaporating flask. Along with that increased evaporation flask size, so you get increased efficiency, more surface area, more can evaporate off at the same time. And overall, what that provides is increased throughput, so you can evaporate more in a shorter amount of time. Again, with upscaling, for both your benchtop evaporator and your industrial size rotary evaporator, you can take advantage of some of those techniques that we mentioned earlier. The pre-programmed gradients mean that you can optimize and preset your evaporation processes so that you don't have to be around to watch them happen. that autonomous vacuum control can be set. So again, it can be efficiently evaporated without you having to be there. It'll work with both your industrial size and your benchtop. And making use of the refill valve, so you're not removing that evaporation flask as often. That way you can save time from having to pull down the vacuum again and the time it takes to remove the evaporating flask, and you can really optimize your process to get as much out of it as possible.
So the next level of upscaling is to make the whole process autonomous. There are modules on the market that allows you to automate everything that you do by hand at the moment. So, for example, these modules can refill your evaporation flask automatically, they can discharge the condensate automatically, and also they can drain off the residue in the evaporation flask when the separation is finished. The advantage of this module is, on the one hand, that you, of course, do not need to be on the rotary evaporator. It can automate your evaporation process, and you can collect in a specific vessel several liters of a specific mixture and can evaporate it in one process, so even overnight or over the weekend. On the other hand, you can always guarantee that the filling level of the evaporation flask is on the most efficient level. So usually if you start the evaporation, it's often too much liquid in the evaporation flask, so the evaporation process is not the most efficient one. With a very low liquid level, you gain the highest evaporation rate per minute, for example, and this can be ensured with these automatic modules that can be sensor controlled, or where you can also set specific time frames where it refills small quantities into the evaporation flask. A nice example from a university here in Germany is that they used to evaporate little samples of a few hundred milliliters every 30 minutes. And when they discovered that there are solutions on the market like that, they decided to buy one and collected all these little samples with the same solvents inside, and started the evaporation process with the automatic module at the end of the day. And on the next days, they have a separation of several liquids, several liters also, without having any efforts, without having any manpower behind, and they have a lot of time saved and also money that they can use for other purposes. And these systems are available not only for benchtop but also for industrial models. That makes sense because especially with industrial models you have a higher throughput, and you can also go into the pilot scale level with these kind of equipment.
Safety is always an important thing when you're evaporating in a lab. It's important with any kind of lab process that you're doing. With your rotary evaporators, there's a couple accessories that you can acquire for really increasing that safety. The first is coated glassware. Your collecting flask and your condenser can all be available with a coating that will help prevent implosion or help prevent shattering in case of dropping it, to really stop any of those glass shards from getting anywhere, or to also increase the longevity of your glassware. Another option is a guard hood. This is particularly helpful when you're running oil in your bath as opposed to water, because it'll prevent any of the splashing that might occur from that hot liquid while your evaporating flask is rotating in there. Kind of shields you from it so nothing hot lands on you or outside of the bath itself. Another really effective tool that you can use is extension cords for your panel. Most panels on modern rotary evaporators are removable, and if you're working inside a fume hood, maybe you want to pull that panel outside the fume hood so while it's running you can control it without having to be in there experiencing any of those conditions. Most modern rotary evaporators also come with internal features to help increase safety. A couple of those include an automatic rise feature, so that if something goes wrong with your process, it'll automatically lift your evaporation flask out of your bath, so you don't have to worry about it overheating or anything bad happening in that regard. Cutouts in case all of the bath water inside your bath evaporates. That way it won't keep heating up, and lead to any potential issues. In that case, it'll just cut out and your unit will stop. Another sometimes overlooked, simple but effective internal feature is a residual heat indicator. Even if your unit's off, if your heating bath is still hot, you'll see maybe a pulsing orange light on your panel to indicate that your unit is still hot. Don't touch it. You know from far away, so that it's just easier to not burn yourself. When running an evaporation process, one of the biggest tips I can give you is to always be in control of your vacuum. It leaves your results more consistent, and you don't have to worry about overboiling as much, and you can really monitor your process. There's a couple different methods of controlling your vacuum. The first, and usually the cheapest, is a manual vacuum controller. This is just a gauge where you can see what the vacuum is, and then leak the vacuum a little bit to keep it at the parameter that you want it to be at. Another option is a digital vacuum controller. This will digitally read what your vacuum is at all times, and then using a valve that's integrated into it, release vacuum every time it gets past the level that you want it to stay at. Lastly, and usually the most effective, is an integrated digital vacuum system, usually with your rotary evaporator all built in. This will make use of a valve and will allow you to accurately control your vacuum through your panel.
Yes, and there are also very modern systems that also can control RPM regulated pump directly. And if you have the choice, I would always recommend to go for the integrated digital vacuum controller, because in the evaporation process, you have different parameters that all have a relation to each other, especially the vacuum and the temperature. And so it makes absolutely sense to have that on one control unit. So it makes also easy for you to save specific favorites, like if you evaporate ethanol very frequently, then you can figure out the one time which parameters you need, and then you can save it and can start it with one button only. So this makes a big step forward regarding to comfortable usage of the rotary evaporator, and also regarding to efficiency in the lab.
Keeping your full rotary evaporator system cleaned and maintained is very important for really increasing the longevity of all of the parts of your process. Cleaning your heating bath is something that's important. Sometimes that water can get gross, or sometimes you'll see some buildup on the side of the heating bath. I recommend replacing the water relatively often, and when you start to see the buildup on the side of your heating bath, I recommend just using some alcohol to clean out the sides of it. Or if you get some really bad buildup, maybe heating the bath up a little bit and putting a little bit of citric acid in there, rotating your evaporating flask so that there's a little bit of turbulence, and letting that sit for about an hour or so. Keeping your glassware is clean is not only important for the longevity of it, but also to make sure you're not getting contamination. There's a couple methods of cleaning it. The quick and dirty way is to run a solvent-only process. That'll kind of flush out the glassware system, make sure there's no products or anything in there. Other methods include cleaning it by hand with a brush, or auto-cleaning it. Maintaining your chiller is important. The methods differ depending on what you're running through there. If you're using the manufacturer liquid, such as Cryo30, it comes with products in there that prevent algae from building up. So you might only need to replace your liquid every year or so. If you're using a home brew of water and glycol, I'd recommend replacing it more frequently, maybe 6 months or earlier, because you run the risk of algae building up in there, and that can really screw with your system. Lastly, maintaining your vacuum pump is really important to always be able to pull down to the maximum rated millibar. Our recommendation is about every day opening up that gas ballast and then just running it without it being hooked up to anything to really dry out the system. Depending on the quality of the vacuum pump, you may be able to do this every week as opposed to every day, but every day will guarantee the best results. One of the most important things to consider with your system is the overall system tightness. The tighter the system is, the easier it is to pull your vacuum down. The tighter your system is, the less contamination you'll get from outside sources, and the tighter your system is, the better your process will run because you won't be rising up in vacuum whenever you're trying to hold. So the first key point when looking through your system tightness is the vacuum seal. A good quality vacuum seal will maintain your tightness for longer, but if you find over time your vacuum starts to fail without anything else changing, that might be the first thing you want to replace. Secondly, if you're using a greased system, you might need to re-grease some joints to make sure that seal is being held properly, or switching to a non-greased system. All of the little caps that are attached to your system, sometimes those seals can move around a little bit. You might just need to unscrew them and rescrew them. And lastly, two other points where you might be losing tightness is making sure the ground joints on the collecting flask are lining up properly with the one on your condenser, and making sure your evaporating flask is pushed all the way up and clamped on nice and tight.
And if you do not find the reason for the leakage directly on the rotary evaporator, it makes sometimes sense to also have a closer look on the periphery devices and periphery materials, especially also on the tubing, that if you use rubber tubing, sometimes the UV radiation over the time leads to cracks inside and can also lead to a leakage inside of the system.
Lastly, sometimes we get the question of what temperature should I run my chiller at? What's important to understand is that bringing your chiller temperature unnecessarily low won't really increase the speed that your process is working at all. So that's why it's really important to follow that delta 20 rule. If your heating bath is at that 60, your vapor temperature is at 40, running it below 20 degrees won't really speed up your process at all. So it's important to recognize that the lower temperature doesn't always lead to a better result. Sometimes running it at 5 degrees is just as effective as running it at -10. And what's important to recognize is that when it comes to chillers, cooling capacity gets worse the lower the temperature is. So while your chiller might say it can go down to -10, when it's fighting against a rotary evaporator, it might not actually have enough cooling capacity to reach those temperatures. So it's always something to keep in mind when you're running your chiller. So don't be surprised if you try to pull down low, but it's a very low wattage chiller.
Thank you, Jürgen and Nate, for a terrific presentation. That was really informative. We have several minutes now for some questions. Audience members, please submit your questions in the Q&A box at the bottom of your screen. And any that we don't get to today will be answered by email. So let's get going with what we have in here. Okay, from Camilla, I have to evaporate ethyl acetate and methanol under 30 degrees C. Ethyl acetate is super fast, but methanol takes ages. How can I speed up the evaporation? I tried mixing solvents, but it's still slow. Who'd like to take that one?
Hello, I'll take that one. So between different solvents, they all have different vapor pressures, so they will evaporate at different speeds. However, to speed up this process, while keeping your bath temperature at the same speed, you can also reduce the vacuum to really get close to that boiling point. Another thing you can do is to keep the flask rotating at the maximum speed you can to ensure that it's evaporating as quickly as possible by increasing that surface area. Now, one solid method that you can use is gradients. That way you can preset the pressure points that you want your solvents to evaporate at, so that you're not just evaporating at the pressure of the lower boiling solvent. This will allow you to maximize how fast each one goes. And then the last thing is that as long as you are at that 3/4 point in your condenser with the recondensing of your solvent, that is pretty much where you will max out if you don't want to pull any into your vacuum pump. So it might just be a solvent that will only evaporate and recondense at that speed. So you can consider either going for a larger sized condenser at that point, or going to a larger unit entirely, such as an industrial-sized unit.
Okay, thank you. Here's an interesting question. What is the typical lifetime of a standard benchtop Rotovape? What parts need to be changed?
That's a good question. I can take over that. It depends highly on the application that you run. I mean, and also on the frequency of use for the rotary evaporator. Sometimes rotary evaporators are only used 1 hour a day or 2 hours, but sometimes they run 8 hours or more a day. So this, of course, got a huge influence into the lifespan of the evaporator. But all in all, we see that for our products, for example, we see and promise 10 years of lifespan. It depends on the parts that are built inside of the evaporator. And of course, you are always in a very aggressive environment. Regarding the wearing parts, for the most quality systems, you only have to replace the vacuum seal. So this is an essential part regarding to services and to also your cost of ownership on a long lifetime.
Okay, thank you. Here's a question from Aaron. How do you recommend rotovaping a sample to remove a lot of water? We have run samples with lots of water and they always bump.
I'll take that one. Thank you very much, Aaron. That's a good question. Water is always going to be one of the more difficult things to evaporate. So it's one of those that you just have to be patient with. You want to increase your vacuum or lower your bath temperature until you're just above that point where it was boiling, and basically just let it run at that point. You might need to increase the cooling capacity on your chiller a little bit, go with a stronger one, because it will take a lot of that cooling out of it because it is so difficult to recondense. The biggest thing is just to be patient with it, sit above that point, potentially switch to an RPM pump so you get a more gentle vacuum, or to use a gradient to pull down to it more slowly and then gradually increase, or I should say reduce the pressure as it goes on to continue to stay below that boiling point.
Okay. And Brianna would like to know, how do you remove product from the evaporation flask at the industrial scale, especially if the final product is dangerous?
Thank you. That's another good question. I can take that one. So you've got the two different methods. One, if you are running a manual process, really the best way you can do it is just removing the flask and scraping it out or dumping it. However, if the final product is dangerous, you most likely don't want to be doing that. And that's a good opportunity to use one of the automated residue removal apparatuses, such as the Distomatic. In that case, when we've had customers that have shared the same problem, such as military applications, where they don't want to have contact with what's left over, or at least minimize it as much as possible, in which case they would use that automatic removal process. The residue pump will suck that out of your evaporating flask, and you can then have that feed into a container that is sealed or marked hazmat or made to contain these kinds of things without having that human contact in between that period.
Okay, thank you. Lots of great questions coming in. Keep them coming, and reminder, we'll answer them all by email if we don't get to them. From Luis, some laboratories use plain water without any antifreezing for the cooling unit. Is this a good idea? I have read that glycerol is a good solution. What is the recommended concentration for this?
I can take that question. Thank you.
Oh, perfect. Thank you, Jürgen.
Sorry, Nathan. Sorry. From a manufacturer perspective, we would always recommend to use that especially developed liquid for the recirculating chiller, because there are also some ingredients inside, like on hygiene protection and things like that, that increase the lifespan and also the cleanness of the tubing system. So we would recommend to use that liquid instead of doing an own glycol mixture. But I know many people do use that, and in the most cases it works as well.
Is that it? Okay. How much surface area of round bottom flask should be immersed in the water bath for proper use?
Thank you. I can take that one. At a minimum, we recommend putting it into the water bath at about the same level that flask itself is filled at. So if the flask is filled to about 1/3 of the way, try to have about 1/3 of the surface in the water bath. You can always put it a little bit deeper, but that's where you'll get, your very good evaporation rate and the good heat transfer between the water bath and the contents of your flask. Anything past that, it's a little bit of diminishing returns, never hurts. Anything below that, you might find a slower heat transfer, which could affect your process.
Okay, great. Chris would like to know, why do you need a chiller when you are using a vacuum pump?
Thank you very much. I can take that one as well. Basically, even though the vacuum pump can lead to you having a lower heating bath temperature, the material still needs to recondense. Otherwise, if you're just using a vacuum pump, you're pulling all of that vapor that you just evaporated off through the pump and into your atmosphere. You're not going to collect much of it at all. That chiller makes it so that it will recondense back into the receiving flask. The vacuum that it is under will reduce the boiling point of your solvent, meaning that it's not going to recondense at room temperature anymore. It's got to be colder in order to recondense.
Okay, thank you. Amit would like to know, what kind of maintenance needs to be done and how frequently to a lab-based rotary evaporator?
Well, I can take over that question. The maintenance depends also a little bit on how often you use your evaporator, but entire cleaning should be done at least all 6 months, I would say, also to avoid any contamination and things like that. But of course, a basic maintenance should be done frequently, nearly every day or every week, to say to clean the most important glassware parts, of course, but also depends on your requirements regarding to your purity of your final solvents, for example.
Okay, thank you. Samir would like to know, can we say all rotary evaporators can be used for purifying alcohol or ethanol? If yes, could you suggest a model from your evaporator range that could be used for purifying a volume of 2 liters or more?
Thank you very much. I can take that one. So ethanol is one of the more easily evaporated solvents. Most of our basic models can handle it. However, because it evaporates so fast, it's one of the ones that you would consider using an automated process for, such as this Dematic. When it comes down to the amount that you want to evaporate, you want to look more at the evaporating flask size and the method of evaporating it than the evaporator itself. If you're looking for 2 liters or more, a 5-liter flask would be optimal for that, or towards the higher size, the industrial sized units would be effective for hitting those. Again, if you want to do more than 2 liters, you can do it in any size of flask if you go with an automated method, because then you don't have to worry about how much is in the flask at each time, because it'll constantly be refilled.
Okay, great. Here's a good question. What's the difference between a vertical and a diagonal condenser?
Yeah, it's a good question. I can take that. I mean, the most important difference is the space-saving aspect that you have with a vertical condenser. Space or available space in the lab is always a big topic, so this can be a very interesting benefit. Moreover, it's slightly easier to identify the height level of the vapor that is rising into the condenser, but this is only a minor thing that might be better. The diagonal condensers are a bit easier to manufacture, and therefore they are sometimes a bit cheaper. So it's about budget. It could be a topic to choose that one. And what we figured out during our tests in-house, we also found out that it helps a little bit to increase the cooling performance as it drops the condensate on the cooling coil, dropped off a little bit earlier due to the diagonal way of manufacturing, and therefore the cooling performance is a bit higher. But this is only a minor thing.
Okay, terrific. A few more questions here. Okay, is there any optimum for the rotation speed?
Hello, thank you for that question. It's a good one. I can answer that. So, for the most part, in most rotary evaporators, the fastest you can spin it is the most optimum. You might want to be careful with the bigger sized flasks. They might have separate recommended maxes for rotation speed, but as far as we have done research on, you won't hit the point where an increased rotation speed starts to hinder your process up until you're above the 300 rotations per minute mark. So for the most part, you would just want to go to the maximum that you can spin your flask that is recommended essentially in the instruction manual or by the company you're working with. Most of the time, you won't actually hit that point where it starts to have a diminishing return.
Okay, thank you. Another question here. Some of my separated solvent gets stuck in the vacuum tubes or inside the vacuum motor. Is there any way to reduce or eliminate this?
Yes, it's another good question. This really comes down to following the rule of not using more than 3/4 of your total condenser for condensing back that liquid. What's happening is that you're evaporating your material potentially too quickly, and it's overriding the condenser's ability to recondense it back into a liquid. When this happens, the vapors themselves are being pulled through the tubing into your vacuum pump because they haven't become a liquid again yet. So, one, follow that 3/4 rule. That would be the easiest, most effective way to prevent it being sucked into your vacuum. Two, you can go with something such as a wolf bottle or a dry ice trap, which is something you would put in between your condenser and your vacuum pump as kind of a second line of defense. That would provide an additional amount of cooling surface and basically just be your fail-safe to prevent any solvent from being sucked into your vacuum pump if it has made it past the condenser.
Okay, thank you. Here's a good question. I am pulling off a high boiling point solvent and a low boiling point solvent out of my evaporating flask. I am keeping the condenser level below 3/4 of the height, but I'm getting solvent sucked into my pump anyway. What is happening and how do I prevent it?
That's a very good question. I've run into this one myself, actually. Basically, what's happening is you're evaporating off that low boiling point solvent just fine. And then to get to that high boiling point solvent, you have to reduce your vacuum pressure significantly further, especially if you are keeping your heating bath constant. Now, what happens as your vacuum goes lower and lower, some low boiling point solvents will actually begin to cold boil, or I should say, they will start to evaporate and boil at room temperature. When this happens, the cooling inside your condenser might not even be at a low enough temperature to recondense that. So what's happening is that as you're evaporating that high boiling point solvent, that's recondensing just fine, but now your low boiling point solvent is being re-evaporated through cold boiling and being sucked through your vacuum pump. The best way to prevent this is to either A, remove your receiving flask and dump it in between the two processes, though that's more inefficient, and B, the better way to where you can keep that process always going is to have a dry ice trap in between your condenser and your vacuum pump, as any solvent that gets re-evaporated will be recondensed from that dry ice trap. Since it's dry ice and acetone in there, you will see that the temperature will be around the negative 76, negative 80 degree mark, and anything that would cold boil at room temperature should surely recondense at that temperature.
Thank you. Okay, a couple more questions. The vapor tube in my rotary evaporator tends to get stuck, and removing it can sometimes result in glass breakage. Is there a way to prevent this?
Yeah, it's a good question, and I can take that. I know that pain point in the lab. Sometimes we face that with many of our customers, and the reason for that is that you have different materials inside of the drive unit that all extend when you start to heat up. The heating bath and the hot vapor rises to this point. And if there are different materials, they also have a different way to extend due to the heat that comes in contact with it, and therefore it sometimes tends to get stuck. There are some systems or clamps on the market. In the newer system, you will find that, especially also in our systems, we have a patented clamping sleeve where we avoid that this gets stuck. So this can be an easy way to avoid that pain point.
Okay, last question here. My chiller specs state that it can run at minus 10 degrees C, but struggles to reach that. Is something wrong with my chiller?
I'll take that one. Thank you very much. That's a good question. So a lot of chillers will have a temperature range in which they can operate under conditions where basically it's feeding into itself. That's just the maximum lowest temperature it can reach. However, in a rotary evaporator system, you're cooling those condenser coils, and that is actively fighting against the vapor that is coming off of your rotary evaporator. In that case, you won't actually be able to reach that optimum temperature because it is continually being warmed up by that vapor. There is a stat in all of your tech specs that will basically be called cooling capacity, and that's about how many watts of cooling it can pull from its system at certain temperatures. As you go colder and colder, it gets harder and harder to hold that temperature, and you'll see your cooling capacity start to reduce. So there'll be an equilibrium point where the fighting between the vapor being evaporated and the cooling of your chiller will meet each other. And that is why you'll find that although your lowest temperature reachable is -10, you won't actually be achieving that. And that's why you usually want to follow that delta 20 rule, because that's around where a nice point that your evaporator and your chiller will meet, depending on the specs of your chiller.
Great. Thank you. That's all the time we have today. Thank you, Jürgen and Nate, for your fascinating presentation. And thank you to the participants who came and were a great audience. Remember the questions that you submitted by email, and there were questions you submitted that we didn't get to, and there were a lot of them, will be answered by email. So be sure to check CNEN or CNEN Online for information on the next webinar. And thank you On24 for your technology and production services. And thank you, Heidolph North America, for the sponsorship that made this webcast possible. For CNEN Webinars, I'm Catherine Dold. Thank you and goodbye.